day, night, and the seasons, how Earth's spin and tilt shape our world. Imagine waking up as the first light of dawn spreads across the sky, watching the sun climb higher, then feeling the air cool as it sinks toward the horizon and darkness returns. That daily rhythm of light and dark is so familiar that it is easy to take for granted. Yet it is only one part of a larger pattern that also brings the long days of summer and the short days of winter. The same slow turning of our planet that creates day and night also, over the course of a year, changes the angle at which sunlight strikes different parts of the surface and the number of hours that sunlight lasts. These changes produce the season and gradual shift from warm growing periods to cold dormant ones, and the dramatic differences between the equator and the poles. Simple observation of the sun's path across the sky, careful measurements of day length at different latitude and time of year, temperature records kept over decades, and photographs taken from space all confirm the same underlying geometry. Earth spins once on its axis every 24 hours, while traveling around the sun once a year with its axis tilt. In the account that follows, we will explore how that spinning and that tilt together create the daily circle of day and night, and the yearly circle of the season. Using clear language and solid evidence that science had gathered, so the pattern of lights and temperature that shape life on Earth become understandable as the sunrise itself. Every lengthening afternoon in spring, every early sunset in autumn, every midnight sun at high latitude, and every equal day and night at the equinox is a direct and measurable consequence of the same two motions acting together. Earth turns on its axis once every 24 hours. The axis is an imaginary line that runs from the North Pole through the center of the planet to the South Pole. Because the planet is roughly spherical, at any moment half of its surface toward the sun and it's illuminated, while the other half faces away and is in darkness. As Earth rotated from west to east, location on the surface moved from the dark side into the light and back into the darkness. Producing the familiar sequence of night, dawn, day, and dusk. The length of the full rotation relative to the sun is what we call a solar day. Approximately 24 hours, this rotation is remarkably steady. Precise clocks and observation of the stars show that the length of the day changes by only fractions of a second over a long period, mainly because of tidal friction with the Moon and the redistribution of mass inside the planet. From the surface, the effect of rotation appears at the Sun rising in the east, climbing across the sky and setting in the west. The path the Sun follows is higher in the sky at midday near the equator and lower near the poles. But the daily cycle itself is caused solely by spinning of the planet. The speed of rotation can be felt indirectly in the Coriolis effect that turns winds and ocean currents. Yet, the most immediate evidence remains the regular daily motion of the entire sky. Time-lapse images taken from fixed camera show the stars and the Sun tracing perfect arcs, confirming that the observer is on a steadily turning sphere. The consistency of this motion also allows the construction of accurate sundials and the division of day into equal hours, practices that have been verified by comparing the Sun's position with modern timekeeping instruments across many latitudes and seasons. The seasons arise from a different motion. Earth's yearly orbit around the Sun, combined with the tilt of its axis. The axis is not perpendicular to the plane of the orbit. It is tilted by about 23.5 degrees. Importantly, the direction of the tilt stays nearly fixed related to the distance stars that as Earth travels around the Sun. As a result, during one part of the orbit, the Northern Hemisphere is tilted toward the Sun, receiving more direct sunlight and longer hours of daylight, while the Southern Hemisphere is tilted away. 6 months later, the situation is reversed. The tilt does not change the total amount of sunlight the whole planet receives, but it redistributes that sunlight between the hemispheres and changes the intensity and duration of light at each latitude. This geometric arrangement is the sole reason for the seasons. The slight ellipticity of Earth's orbit, which brings the planet a few percent closer to the Sun in early January and farther away in early July, has only a minor effect and actually works opposite to the seasons in the Northern Hemisphere. The dominant cause is axial tilts. The amount of energy received at the top of atmospheres can be calculated from the solar constant, the distance to the Sun, and the angle of incidence. These calculations match satellite measurements of incoming solar radiation to high accuracy and show that the seasonal contrast is produced almost entirely by changing geometry of the tilt rather than by the small change in distance. For any given latitude, The daily total of solar energy can be computed by integrating the varying solar elevation over hours of daylight. The resulting curves peak sharply at the summer solstice and drop to the lowest value at the winter solstice, matching records collected by parameters at weather stations worldwide. When a hemisphere is tilted toward the sun, two things happen once. First, sunlight strikes the surface at a steeper angle, so the same amount of energy is concentrated on a smaller area and heating is more effective. Second, the sun stays above the horizon for more than 12 hours, giving the surface a longer time to absorb energy. In the opposite hemisphere, the sun rays arrive at a shallower angle, spreading energy over a larger area, and the day is shorter than 12 hours. At the equator, the day length remains close to 12 hours year-round, and the sun's midday height changes only modestly, so seasonal temperature contrasts are small. Toward the poles, the contrasts become extreme. Around the time of June solstice, the North Pole is tilted fully toward the sun and experiences continuously daylight for months, while the South Pole is in continuous darkness. 6 months later, the roles reverse. This period of polar day and polar night are direct consequences of the tilt and are observed every year. The continuous daylight of the solar summer allows the surface to accumulate heat even though the sun remains low. Because the energy input never stops. In the polar winter, the absence of any sunlight allows temperatures to fall rapidly, limited only by the heat stored in the ocean and the atmosphere and by the weak downward infrared radiation from the air. For example, at a research station near 80 degrees north latitude, the sun remains above the horizon for more than 100 continuous days around the June solstice, delivering a daily energy total that can exceed the midsummer total at 40 degrees latitude, simply because there is no night. In contrast, the same station experienced more than 100 days of continuous darkness around the December solstice, during which surface temperature routinely dropped below minus 30 degrees Celsius, even though the station sits near sea level. Similar records from Antarctic bases show even lower winter temperature because the high ice sheet and the surrounding cold ocean provide less stored heat to moderate the long night. During the transition periods of polar twilight, the sun remains just below the horizon for weeks, producing a prolonged soft light, and still contributes measurable energy and allow limited outdoor activity, a phenomenon documented by both ground observers and satellites that track the gradual advance of the thermometer across the polar regions. The transition points between these extremes are the equinox and solstice. At the equinox, which occur around the third week of March and the third week of September, the axis is tilted neither toward nor away from the sun. Day and night are approximately equal in length everywhere on Earth, and the sun rises due east and sets due west. In reality, the day is a few minutes longer than the night at most latitude because the sun is a disk rather than a point, and because Earth's atmosphere bends light, allowing upper edge of the sun to be visible before the true geometric sunrise. At the solstice, around the third week of June and the third week of December, the tilt reaches its maximum effect. One hemisphere has its longest day and highest midday sun, while the other has its shortest day and lowest midday sun. Measurement of day length at any fixed location show a smooth annual curve that peaks at the summer solstice and reaches a minimum at the winter solstice, exactly as predicted by the tilted geometry. The exact dates of the solstice and equinox shift slightly from year to year because the calendar year is not an exact multiple of the orbital period. Yet the underlying astronomical events remain precisely determined by the orientation of the axis relative to the sun. The changing angle of sunlight also affects how much atmosphere the rays must pass through. When the sun is low in the sky, its light travels a longer path through the air, so more energy is scattered or absorbed before reaching the ground. This is why sunlight feels weaker in winter, even at midday, and why the sky near the horizon often appears redder at sunrise and sunset. The extra path length can be calculated from the solar elevation angles. At the elevation of 10 degrees, the path is more than 5 times longer than when the sun is overhead. Temperature records from weather stations around the world show that average temperature rise and fall in step with the changing day length and solar angle, with a lag of several weeks because the land and especially the oceans take time to heat up and cool down. Coastal regions in the Southern Hemisphere, which is dominated by ocean, have milder seasonal swings than continental interiors at the same latitude. Again, consistent with the greater heat capacity of water, snows and ice cover further amplify the seasonal contrast by reflecting most of the incoming sunlight, so that once winter snow is established, the surface absorbs even less energy and stays cold longer. In continental interiors, such as Central Asia or the northern Great Plains, the temperature difference between the warmest and coldest months and exceed 40 degrees Celsius, while at the same latitude on a west coast, the range is often less than 15 degrees, illustrating the moderating influence of the ocean's thermal inertia. Evidence for the rotation and the tilts comes from many independent observations. The daily motion of the sun, moon, and stars across the sky is the most immediate proof of Earth's spin, while time-lapse photography and simple sundials show the same regular westward movement. The length of the day can be measured with great precision by timing the intervals between successive trances of the sun or of a star across a meridian. Modern atomic clocks confirm that this interval is stable to within milliseconds. The axial tilt is revealed by changing height of the midday sun through the year. At any mid-latitude location, the sun climbs higher in sky each day from the winter solstice to the summer solstice, and then descends again, a pattern that can be tracked with a simple stick and the length of its shadow. The maximum and minimum shadow lengths yield the exact value of the tilt when combined with the observer latitude. Satellite images of Earth show the terminator, the moving boundary between day and night, sweeping around the planet every 24 hours. And they also show how the polar regions remain fully illuminated or fully dark for months at a time. The same images capture the gradual shift of the terminator orientation related to the poles as the seasons progress, providing a global view of the changing geometry. The distribution of solar energy across the globe can be calculated from basic geometry once the tilt and the orbital position are known. These calculation maps measures values of solar radiation recorded by ground instruments and by satellites. At the summer solstice, a mid-latitude location in the Northern Hemisphere can receive more than twice as much solar energy per day as it does at the winter solstice, primarily because of the longer day and the higher sun angle. Near the poles, the contrast is even greater. Continuous sunlight for months versus continuous darkness. Temperature data averaged over many years show that the warmest and coldest month lag the solstices by about a month in most places, confirming that the surface and atmospheres take time to respond to the changing energy input. Ocean temperatures lag even more, which is why the warmest sea surface temperatures in the Northern Hemisphere often occur in August or September rather than June. The lag is the direct consequence of the heat capacity of water and the depth of the mixed layer that must be warmed or cooled. In the upper 50 to 100 meters of the ocean, the temperature responds over weeks to months, while deeper layers change far more slowly, storing the seasonal heat surplus and releasing it gradually. The combination of rotation and tilt also produce the familiar progressions of sunrise and sunset directions. At the equinoxes, the sunrise due east and set due west at every latitude. Between the March equinox and the September equinox, the sunrise and sunsets points shift northward in the Northern Hemisphere, reaching the northernmost position at the June solstice. After that, they migrate southward again. Observers who mark the position of sunrise or sunset on the horizon throughout the year see a smooth annual oscillations whose amplitude increase with latitude, exactly as expected from the fixed tilt of the axis. The azimuth of sunrise at the solstice can be calculated from observers' latitude and the tilt angle, and the predicted position match measurements made with surveying instrument or even with simple landmarks. This annual migration of the sunrise and sunsets points is one every inhabited regions. points in one of the most accessible demonstrations of the axial tilt and has been recorded by cultures in every inhabited region. At 60 degrees latitude, the sunrise point at the summer solstice lies more than 40 degrees north of east. The shift large enough to be noticed without instruments and to affect the designs of buildings and the orientation of agricultural fields. At the poles, the effects of tilt become absolute. For roughly 6 months, the sun never sets, circling around the horizon once every 24 hours without dipping below it. For the other 6 months, the sun never rises. The transition periods near the equinox produce weeks of twilight as the sun skims just below or just above the horizon. These polar day and polar night conditions have been documented by automatic weather stations, by research bases, and by satellites that remained in view of the poles for extended periods. The continuous daylight of the polar summer allows temperatures to rise above freezing even though the sun remains low in the sky, because the energy input through wick per hour continuous without interruption. In the polar winter, the long darkness allowed temperature to plummet, since no polar energy arrives at all. The duration of polar day and polar night increase with latitude inside the polar circles, reaching a full 6 months at the poles themselves. Measurements of solar radiation at polar stations confirm that the daily total during continuous daylight can exceed the daily total at lower latitudes in summer, simply because the sun never sets. The same geometry explains why the seasons are opposite in 2 hemispheres. When the Northern Hemisphere is tilted toward the sun and experiencing summer, the Southern Hemisphere is tilted away and experiencing winter. 6 months later, the situation reversed. Temperature records from stations in both hemispheres confirm these oppositions. The warmest months in the north are the coldest months in the south, and vice versa. The Southern Hemisphere seasons are slightly milder on average because a larger fraction of its surface is ocean, which moderates the temperature swing. But the timing is precisely 6 months out of phase with north. The difference in land-ocean distribution also explains why the Arctic winter is colder than the Arctic winter, and why the Antarctic summer remains cooler than the Arctic summer. The high Antarctic ice sheet and the surrounding ocean creates a more extreme thermal environment. Day length itself varies with latitude and season in a predictable way. At equator, the day is always close to 12 hours. At 60 degrees latitude, the longest day exceeds 18 hours and the shortest is less than 6 hours. Beyond the polar circles, the longest day becomes continuous light and the shortest becomes continuous darkness. These values can be calculated from spherical trigonometry once the tilt and the observer latitude are known, and they match direct measurement of sunrise and sunset times published in almanacs and recorded by automatic sensors. The gradual lengthening and shortening of the day is what drives the seasonal cycle of plant growth, animal migration, and human agriculture calendar in every inhabited region. The rate of change is fastest near the equinox and slowest near the solstice. The pattern that can be felt at the rapid lengthening of evening in early spring and the slower change in midsummer. For instance, a latitude of 45 degrees, the day length increased by nearly 3 minutes every day around March equinox, while near the June solstice, the daily change shrinks to less than 30 seconds, giving the sensation of that summer days stay long for an extended period before beginning their slow decline. This rapid change near the equinoxes is also visible in the quick shift of summer sunrise and sunset times that many people notice in the weeks around March and September. The atmospheres and the surface respond to these changing energy inputs with a lag. Land heats and cools quickly, so continental interiors show large temperature differences between summer and winter. Ocean heat and cool slowly, so maritime climates have smaller seasonal range and their temperature peaks occur later. Mountains, snow cover, and vegetation further modify they respond by altering how much sunlight is absorbed or reflected. Snow and ice reflect most of the incoming energy, reinforcing cold conditions, while dark forests and bare soil absorb more. These feedbacks are observed in satellite record of surface reflectivity and in the temperature data from high latitude stations. None of them alter the fundamental cause. They only amplify or dampen the effects of changing solar geometry. The overall energy budget of the planet remains balanced over the year, but the seasonal redistribution of energy between hemispheres and between surface and atmospheres produce the familiar progressions of the season. In regions with extensive seasonal snow cover, the spring melt itself release additional water into rivers and soils, linking the light circle to the water circle and further illustrating how the geometric change drive multiple environmental responses. The regularity of the day-night circle and seasonal circle is itself evidence of the stability of Earth's rotation and orbital motion. Atomic clocks and astronomical observations show that the length of the day changes by only milliseconds over years, and the tilt of axis changes by only tiny fractions of a degree over centuries. These slow variations are measurable, but far too small to affect the daily or seasonal patterns on human time scales. The dominant signals remain the 24-hour rotation and the yearly orbit with its fixed tilt, producing the reliable succession of day and night, and equally reliable progressions of the seasons that living organisms have adapted to over millions of years. The same stability allows precise prediction of sunrise and sunset times, day lengths, and the date of solstices and equinoxes year in advance. Prediction that match up observation to within seconds. In this way, the simple facts of Earth's spin and its tilt axis is account for the entire range of daily and seasonal light patterns observed across the planet. The sun rises and sets because the planet turns. The days grow longer and shorter. The midday sun climbs higher and lower, and the poles experience months of light or darkness because the axis remains pointed in the same direction while the planet travels around the sun. Measurement of day length, solar angle, surface temperature, and the distribution of sunlight from space all align with its geometric to high precisions. The pattern of light and temperature that shape climates, ecosystem, and human activity are therefore the direct and predictable consequence of the planet rotation and its orbital tilt, continuing unchanged in their essential character for as long as those motions persist. Every observed variation in the length of the day, every measured change in the height of midday sun, and every recorded shift in seasonal temperature follows from the same two motion, confirming that the daily circle of light and dark and the yearly circle of the season are two inseparable expressions of Earth's places in the solar system.